Making good progress here. So we'll keep moving along. Got an example here. This is going to be lecture 18. We've got page 1 of something. So let's work an example, shall we? We've just talked about the second law of thermodynamics. We've introduced the concept of an isentropic situation, and let's see if we can put some of those ideas to work. So, um, I'm going to write down these givens on my paper here, and then we'll switch from presentation mode to the document camera here, and we'll work this problem out, at least set it up. You've got saturated R134. So given, we've got R134A. You've got saturated R134 vapor enters. So that means I'm just going to write that X1 is equal to 1. That means that's shorthand for saying saturated vapor. X means it's saturated, it's the quality. 1 means it's 100% in the vapor phase, so it's saturated vapor. You can write that out in words if you like. I'm just going to write X1 is equal to 1. So saturated vapor enters an adiabatic compressor. The minimum power input to the compressor is to be determined. Also determine the exit temperature. Okay. Now, something I've not talked about in these videos yet is how do we know when something's reversible? So if we look back at our notes from lecture 17 here, and I said that if I've got a reversible process, right, in a reversible process, that that means this S gen is equal to 0. But what does that mean? How do we know that? Well, if it's reversible process, this means it's the best version of the process. Now, that can come in a number of different forms, but often it's going to be something like the minimum input or the maximum output. You have to really focus on what is the device trying to do. In the case of a turbine, for example, or a turbine, for a turbine, you're trying to get work out. So the best possible version of the turbine would be the one that has the maximum output, right? You don't want the turbine with the minimum output because a turbine not running would be generating zero work. So the minimum work output doesn't make sense. You really have to think about what is the purpose of the device, and is the problem statement telling me this is the best possible version of this device? If it is, then it's telling you you can assume that it's reversible and that S gen is equal to 0. Now, don't get stuck on max or min or maximum or minimum. That's not what you want to get stuck on here, right? What you want to be thinking about, though, is what is the purpose of the device? Have they told me in the problem statement that I'm looking at the best possible version of the device? And here they are, right? Notice this word right here. All that discussion to talk about. Notice this word right here, minimum input. It's a compressor. So a compressor that requires the least amount of work input tells me that it is reversible, meaning it's not generating entropy. Right? So again, what is the adjective telling you? Don't get stuck on minimum and maximum. Think about is that telling me that's the best version of this device? The compressor that requires the minimum input is the best possible compressor. That is the reversible compressor. That sets the limit. Um, so again, we want to determine the minimum power input to the compressor, and we want to determine the exit temperature of this compressor. So, have I missed any? Well, I've got some other givens they've given to me here, right? They've said it's often with a compressor or a turbine or a turbine, you're probably going to know the inlet and outlet pressures. It's not a give, like it's not a guarantee, but there's a good chance you will. A lot of times, a compressor, you're after that pressure change. You're after a higher pressure at the output, is really what you're after. Now, the problem statement here probably would tell us in words that the saturated vapor enters the compressor at a rate of 2 cubic meters per minute, or whatever appropriate information there. They're probably not going to tell you it's V dot. You're going to have to figure that out from the units, but they're going to tell you the rate at which it's entering or exiting the device. And that's so you're going to have to look at the units or what's given to you and figure out, is that an M dot? Is that a V dot? Is that a speed? What is that? Um, so that's what's given to us in this one. There is something else that's given to us that I've not written down yet. It is adiabatic. It is adiabatic. So Q is 0, right? So that's, don't let that one sneak up on you. Okay. So I'm going to stop share and let's set this guy up. Well, I guess I didn't write down what we're looking for, did I? What are we looking for? We want to find, that's always the first place we want to start. Problem solving 101. What are you looking for? I want to find the work input, the minimum work input. The minimum is handled here. Find the work input and also find the temperature out. We want to know, how hot is this refrigerant coming out? Is it going to be hot enough that it's actually going to do what we need it to do in the rest of the device? Probably some kind of a refrigerator. Okay, so all right, well, how do we start? What's a good place to start? How do we go about finding either? And it does say the power input, so it's going to be a W dot is what we're looking for. How do we go about finding the power input? And well, that's an unknown energy quantity. How do we find an unknown energy quantity? First law. So what is the device? The device is a compressor. And so the device is a compressor. So got an outlet at kind of the narrower end. I like to draw a compressor in this turbo configuration. So I'm putting a power input there, and I've got mass coming in the kind of the wider end and getting pushed out the more narrow end. So it's getting squeezed as it makes its way through this. It's getting squeezed further and further. That's how I normally draw a compressor. That's how I was taught to. If you want to draw it as a piston cylinder with mass crossing the boundary, that's fine. That's how your book does it. This is normally how I draw a compressor. Anything else crossing the boundary? Any other energies? I've got mass, I've got power, I've got mass. I'm looking for the power inputs. I'm not so concerned about a power output. There's not really anything pulling power out. The other thing that can cross, you got work, mass, and the other thing could be heat transfer. And again, we know it's adiabatic, so there's no heat transfer here. So I've got power in plus E dot mass coming in minus E dot mass going out. So we did this in chapter 5, talking about writing a first law equation. This is a steady flow control volume, or at least I'm going to assume this is a steady flow control volume. So I'm going to set the change, the right-hand side, equal to 0. All right, so how do we quantify this? Well, got power input. I've got one inlet, one outlet, so it's going to be a common M dot between those two. Again, we talked about this in chapter 5. These are going to have enthalpies and kinetic energies. So I know I'm going to have an enthalpy change, H1 minus H2, that's in minus out. Now, do I have a kinetic change? And that one I don't know about. Let's look and see. We had a checklist we talked about earlier about how do we know if there's a kinetic change? Well, they didn't, it's not a nozzle or diffuser, so we may not have to find the kinetic change. It's not given, the speeds aren't given, and it's not asking for a change in speed. So I think we're going to assume that the change in kinetic energy is negligible. We don't really have any other way to deal with this. So we're going to set that equal to 0. So that's the first law set up. And if we go through and look and say, all right, well, can we solve this? I'm looking for the power input. Right? That's this guy. Is that my only unknown here? Well, I don't know. Do I have M dot? I don't have M dot. But I do have the conservation of mass as kind of normally a very good way of getting to that. And we know M dot at any point is equal to, well, notice here I do have volumetric flow rate. So I've got volumetric flow rate at the inlet, and I might be able to find the specific volume at the inlet. If it's a liquid, I might use the density, but since it's a vapor and I've got property tables for R134, I'm going to use a specific volume here, I think. So this would allow me to get m dot. What about H's? Well, again, H's are property. Uh, that's going to be dictated by what the substance is. The substance is R134A. I've got property tables for that. To use those property tables, I need to know two states or two properties at each state. Well, I know pressure at both states. And I also know that it's saturated vapor at the inlet. So I can use that. I can use P1 and X1 to find H1. I'm also going to need V1 while I'm there. All right, what do I know at state 2? Well, I know P2 at state 2. I know P2. If I go back and look at my givens, and the rookie mistake is to say, Steve, it's saturated vapor. Isn't it saturated vapor at the exit? No, we don't know that. We don't know anything about whether it's vapor or superheated vapor, saturated vapor. We don't know what it is. We know it's probably vapor, but we don't know saturated or superheated. If I knew the temperature, I could verify whether it's saturated or superheated, but I don't know the temperature. So I don't know the temperature. I don't have specific volume. I need H2 is what I'm after. So I can't solve for H2 because I also need to solve for this. So is there anything else that would help us allow us to figure out a property at state 2 so I can get H2? And here's where I would say pause the video here and think about, okay, well, given look at your notes, what you've got there. Is there anything that would help you get a second property at state 2 based on maybe even on things that we've talked about recently? So go ahead and pause and see if you can figure that out. How am I going to get a second property at state 2? All right, so either you've given up or you've got an answer. I don't know which it is, but let's talk about how do we get state 2? Well, we've shown you, here's the first law. We've looked at conservation of mass. And what is the whole purpose of this chapter? Well, this whole chapter is about the second law, right? So if we look at the second law, and what the second law does for us, remember this is a process from state 1 to 2, and this one has a mass flow rate, right? So we've got flowing mass in this one. So I guess we could use, it really doesn't matter which form of the second law we use, but we might use this one that's got the mass flow rate. So m dot times little s2 minus little s1 is equal to the integral of dq dot over t from state 1 to state 2 plus the rate at which entropy is being generated, big S gen dot. All right, well, I can find m dot. We've already described that earlier, right? I can find m dot. You know what? If I can get these two properties at state 1, I should also be able to get S1. So I can get S1. You know what? If I know S2, that gives me my second property, doesn't it? So can I find S2 based on what I know? Well, all right, look here. Can I quantify the heat transfer? What do I know about the heat transfer? Well, you go back to the problem statement, and it says it's adiabatic. Q is 0. This is what we talked about a little bit ago on the previous example in lecture 17. This is saying add up everywhere you see heat transfer and divide that heat transfer by temperature. If I add up all the zeros of that are heat transfer, I'm going to get 0, right? So if it's adiabatic, well insulated, this integral dq over t goes to 0. And do I know anything about the entropy that's being generated? Well, yeah, they told me that I wanted to find the minimum input for this compressor. So compressor requires a work input to increase the pressure and increase the energy of the fluid stream. The best possible compressor is the one that requires the least amount of work to do so. That means it's a reversible compressor. So that means S gen is 0. So that means S2 minus S1 is equal to 0 divided by m dot, which is still just 0, or S2 equals S1. Remember, I wrote this out earlier. I said, if you know it's adiabatic, I think we talked about this in lecture 17. If it's adiabatic and it's reversible, if I know those two things, that tells me it's isentropic. I made a big deal, and I'll continue to do it, about just because I know it's isentropic doesn't mean I know it's adiabatic and reversible. This could be negative and this could be positive, and they can cancel each other out, and this could still be zero. But if I know this is zero and I know this is zero, then that tells me delta S is zero. All right, this video will be a little longer than 15 minutes, and that's okay. So if I know it's adiabatic and I know it's reversible, then I know it's isentropic. And that's what we have here. I have S2 minus S1 is equal to zero, or S2 is equal to S1. So if I get S1, then I can set S1 equal to S2. And then these two properties would be enough to get me H2. And notice the problem statement also asked me for the exit temperature. So I'd also need to be able to get T2 from that information. Okay, so here's where I would say pause, go look up these properties in your property table, and I'm going to switch over and share screen, and I'm going to start displaying these properties. But pause and make sure you can go look these up and see if you can figure out how to get these values. Okay. All right, hopefully that was long enough for you to pause to go look these up. Right, again, I've got saturated vapor at the initial state. Okay, so saturated vapor at the initial state. And so I go look up saturated vapor at 160 kilopascals. That gives me state one properties. So those are here, right? And then I want to get state two. So if you don't already have state two, pause and figure out how you're going to get state two. Okay, so how do we get to state two? Well, if you go look, notice we're using this entropy value, 0.9419. 941, and you might have something different. This is an older edition of the text, and the R134 values do change a little bit from edition to edition. But I'm using 9419 here for S2. So I'm looking at this pressure. So 0.9 megapascals, 900 kilopascals. I have 9419. That's going to be between these two entropy values. So that means my enthalpy is going to be between these two values. Looks like it's probably closer to this 274. And my temperature is going to be between these two values, probably closer to 40. I'm going to have to interpolate between these two rows for both temperature, which is one of the answers the problem's asking for, is just to find the exit temperature. So I'm going to have to interpolate a temperature between 40 and 50. And I'm going to have to interpolate an H2 value between 274.17 and 284.17. Okay, so go ahead and pause it. If you haven't already done that interpolation, that's good practice. Go ahead and do that real quick and then come back with your answer, okay? All right, you got your answer? This is what I've got. That's, again, was between 270, H2 should be between about 274 and 284. So we're getting 277.1. We expect it should be closer to the lower value because the entropy was closer to the lower entropy value. And it should be closer to 40 degrees C. We get about 42.75 Celsius. Should get you pretty close. So that gives us our 2H values, which is what we needed to solve our first law equation. Again, we have specific volume at state one. That gives us m dot with our volumetric flow rates. We've got m dot. We have both H's. Solve for the power input, and we're good to go. Right? We got these goofy units on the V dot per unit per minute. So make sure you throw a factor of 60 in here, right? Right, times 1 minute for every 60 seconds. Make sure you throw that on there. And that should get us then, that would be meters cubed per second on top, meters cubed per kilogram on top. On bottom, it gives us kilograms per second, about a little more than a quarter of a kilogram per second. And in order to maintain this pressure change with this flow rate of mass for this compressor, we're going to need at least 9 kilowatts of power. And at least 9 kilowatts. It's 9,000 watts. That seems really high. I don't know if that's realistic or not. It might be a really big system, but anyway, hopefully that helps, right? So two answers there. The power input, that's the minimum power input. This gives us an idea. All right, if you need something this big, this gives you a minimum amount of power input in order to achieve that. And it also gives you an idea of what the exit temperature ideally could be at the outlet. So it needs to be in an environment If it's going to another heat exchanger after this in a refrigeration system, it needs to be in an environment where it can still lose heat at that temperature. All right. Hopefully that helps. It's a nice example. It's a little longer than 15 minutes on this, a lot longer than 15 minutes on this video. So I'm going to stop this one here and we'll move on to the next one.